Okay, so the time limit on these videos when we use a screencast-o-matic is 15 minutes, so got cut off there. So the second part of the answer key, getting back to our one variable inequality. So like I was saying, remember, you're finding the x value that doesn't make this equation true. You're finding the x value that's the boundary of the x values that makes this inequality true. So what x value um, is the boundary for which values are greater than or less than that make this true. So for example, on this one, we're going to solve this just like an equation to find that boundary. So on this one, when we solve that just like we would any other two variable equation, we get x equals 6, although it's an inequality, so it is x is greater than 6 when we solve that. I'm skipping the two solve steps because that's something that we should all be able to do, adding 5 to both sides, dividing both sides by 2. And then to represent this on the number line, we're just going to pick a place to put 6. I'm going to put it right there. It really doesn't matter where you put it. You're just identifying where you are on the number line on this graph. So if this is 6, any value of x that's greater than 6 is going to make that inequality true. So I'm using an open dot because it doesn't include the value of 6. If I put 6 into that inequality, I would get 7 is greater than 7. That's not true. But if I put a number that's greater than 6, let's say I put 10 into that inequality, I would have 20 minus 5, which is 15, is greater than 7. 15 is greater than 7, so it makes it true. If I picked a number that was less than 6, like 0, I would have negative 5 is greater than 7 if I substitute in 0 for x. And negative 5 is not greater than 7, so that's not true. So this is how we represent the values of x that make that inequality true. The second inequality has a couple of extra steps. So for example, to solve for x, we need to distribute. And so we end up with 12 minus 3x is greater than or equal to 18. So on this one, when you subtract 12 from both sides, again, solving for x, just like you would in an equation, we end up with negative 3x is greater than or equal to 6. And this is the only spot in a one variable inequality where the rules are different, because right here where we're getting x by itself by dividing both sides by negative 3, when you divide or multiply both sides of an inequality by a negative number, what was positive is negative, what was negative is now positive. In effect, it kind of flips the number line over, and the relationships between the expressions, values, or terms on either side. And so we need to flip over the inequality sign to reflect that. So when we divide both sides by negative 3, we get x is less than or equal to negative 2. And so graphing this one, I'm going to pick a spot for negative 2. I'm going to put it, I'll have it right there. And it doesn't matter, you're just saying where you are on the number line. Shown, less than means it's going to go down the number line to the left. And again, if you're not sure, you can always test these out. Just like with an equation, if you solve for the value of x that makes it true, you can put that value into your equation, evaluate it, and see if it makes the equation true. You can do the same thing with an inequality. So if we picked a number that was, for example, less than negative 2, so let's say we picked negative 3. If you were to put in a negative 3 in for x into the original inequality, so if x was a negative 3, we would have 4 minus negative 3, which is 7. 3 times 7 is 21. 21 is greater than or equal to 18. So negative 3 right here makes that inequality true. If I picked a number like, let's say 0, a number that's greater than over on the other side of negative 2, if I put a 0 in for x, I get 3 times 4 minus 0, which is 12. 12 is greater than or equal to 18. That's not true. And so any other number on that side of the dot is going to make that inequality false. The very last one is a compound inequality. And so there's actually no calculations to do here. All you have to do on this one is identify where negative 2 and 5 are. So I'm going to put negative 2 here, which means 0 would be there, and 2, 3, 4, 5 would be here. Open dots because they are both less than but not equal to signs. And you connect those, and notice we look at the inequality. X is greater than negative 2 and less than 5. So it basically says x is between negative 2 and 5. And that's what our number line shows. So this is a compound inequality where you have 2 points on the number line, and the solutions to that compound inequality are either the values in between those points, which is the way this one works, or it's the values outside of those points. So it's every value on the number line except for the values between them. But that would look like a different compound inequality. That was an above standard optional exercise. So you can always go back to those in the stuff that was offered before the schools were closed. Okay, moving on. On these ones, when you graph an inequality, you're going to graph it just like you would graph a standard form or slope-intercept equation to start out with. So sorry, I'm going to get rid of some of my work here and kind of work through it. This isn't so cluttered up. And so that's what I've got right here on the inequality on the left. I just graphed 2x minus 4y equals 12 as if it was an equation using the x-y-intercept. So if x is 0, y is -3. If y is 0, x would be 6. So I got those two orange dots, connect them with a solid line because this inequality sign is greater than and equal to, which means points on the line make this inequality true. So graph it just like a line. The thing that makes a difference when it's an inequality is that line is now a boundary of the regions of the graph that contain the xy combos that make it true and the xy combos that don't. So to decide which side to shade, use a test point. I always recommend using the origin right here at 0, 0, just because it's the easiest one to do calculations with, especially in standard form. So if I put 0, 0 into my inequality, I get 2 times 0 minus 4 times 0 is greater than or equal to 12. And so when I put 0, 0 in other words, that just makes the left side 0. The right side is still 12. Now notice that is not true. 0 is not greater than 12, greater than or equal to 12, which means points, including the origin, but points on that side of the line make this inequality false. So if this point makes the inequality false, every other point on that side of the line makes the inequality false. That means the other side of the line contains the xy values that make this inequality true. And you could pick any coordinate point off of this side of the line that I've shaded in blue, put the xy value into that inequality, and it should make that inequality true. I'm going to leave that part up to you if you want to do that. The second one, again, I'm going to get rid of some of the work that I did as I was making the answer key. The second one, what you want to start out by doing is, write the equation for the line just like you would for any other line. And slope-intercept form is the easiest way to do that. But instead of an equal sign, I'm just going to make an empty box there for the inequality sign. And I'll talk about how you decide what inequality sign works. Just a quick recap, though, I kind of pre-did some of the work here. I did the equation for that line, this dashed line in slope-intercept form. 0, 1 is my slope, so that's where I got the 1. And then from point to point, just going from the y-intercept on down to the right, going down 1 over 2 to this next whole number coordinate point. That's a slope of -1 over 2, -1/2. So that's where I got this slope-intercept equation from. What we need to decide is this a greater than or a less than inequality? And so again, we're going to use a test point. So you could use 0, 0 as a test point. You could use any value as a test point. So I'm going to show a couple ways to do this. On this one, I think I'm going to use, how about 0, -1? So I'm going to use this point as a test point. I'm going to pick a point on the side that makes the inequality true, and I'm going to put that value into my equation. So at that point, y is -1. Again, we don't know what symbol goes there. And x is 0 at that point. So I've got -1/2 times 0 plus 1. So if I simplify this, I get -1, and then -1/2 times 0 is 0, plus 1. So I end up with -1 on the left, +1 on the right. So now what inequality sign makes the relationship between those numbers true. And so -1 is less than +1, so this should be a less than. So that should also be a less than in the original equation up here. So this should be less than. Okay, now if I had chosen a point on the other side of the line, so I'm going to choose a nice simple whole number coordinate point on the other side of the line, I'm going to choose, well, let's say 1, 3 on the other side of the line. So if I were to put that one into my original equation, so y at that point is 3, -1/2, and then x at that value is, at that point, is 1 plus 1. If I simplify that, I get 3. And then this would be -1/2 plus 1. That would be +1/2. Now notice, 3 is greater than 1/2. So the inequality symbol that would make this inequality true would be a greater than symbol. But remember, in this graph, that point is on the side of the line that contains the points, the x, y values, that make that inequality false. So if I was to choose that point, trying to decide what inequality sign I need to include for my inequality to represent this graph, I would want an inequality sign that makes this false. Again, it leads me to that should be a less than symbol, because that point, when I put the xy value in, makes the inequality false. And this point, the other one that I chose previously, that one makes the inequality true. So notice, in both cases, a less than symbol makes that inequality true.